All right, hey everybody. Today we're going over the rest of 12.2, which is kind of some applications of vectors. We're talking about force and resultant force and stuff like that, and angles made with the positive x-axis and all that good stuff. So here we go. Today's lesson was brought to you by the letter pi and also the number pi. Let's see. So here we go. Finding the angle made with an axis. So, first example, well, I guess we'll write the top 12.2. Continued. Okay, so first type of problem, find the angle made with an axis. Typically, wow, that was bad. There we go. Typically, the positive x-axis. Okay, so we're going to use the vector 8i plus 6j. All right. So if I want to find the angle made with the positive x-axis on this one, first off, this is just a two-dimensional vector here. And so I can just plot this real quick. All right, so I represents the x component. So it's going to be over 8. J represents the y component or the vertical component. So that's going to be 6. This is the vector we're dealing with. And if I drop a perpendicular down here, we've got a right triangle with sides that are lengths 8 and 6. So if I want to find the angle that this thing makes with the x-axis, that's the angle we're looking for. So we can just use right triangle trig. Looking at that angle, we have the opposite side and the adjacent side. And opposite and adjacent implies that we're going to use tangent. So we know that tangent of that angle is opposite over adjacent, or 6 over 8. And we just do inverse tangent, and we have our angle. So the angle we're looking for is inverse tangent of 6 over 8. And then we type that into the calculator. Inverse tangent of 6 over 8. If you want it in radians, that would be 0.644. And then in degrees, we get 36.870 degrees. All right. So that's finding the angle made with the axis. That's typically not all we're going to end up doing when we're dealing with vectors and things like that, but it's a good start. So the next thing we're going to do is talk about a resultant force application. So here we go, resultant force. All right, so let's say we have two forces here. We'll call them F1 for our first force vector and F2 for our second force vector. The first force vector, actually, we're going to draw these out. So our first force vector, F1, is a 10-pound force. And it makes a 60-degree angle with the positive x-axis. And then our second force vector is a little bit longer. It's a 15-pound force. And it makes a 45-degree angle. Right there. Okay. So now we want to figure out what's the resultant force of both of these vectors acting on the same thing. So in order to do that, we have to express these forces in terms of their horizontal and vertical components. So that means we got to represent them with I and J and stuff like that. The horizontal component of the first one is 10 cosine of 60 degrees. So this 10-pound force represents this this vector length here. And so if I go 10 cosine 60, we get this horizontal component because cosine goes with x, sine goes with y. So that's where we get our horizontal component. And then likewise, the vertical component is going to be 10 sine 60. J. All right. Then our second force vector, we're going to express in the same fashion. For this one, though, it's going to be 15 cosine of 45 for the horizontal component. And then since our vertical component is going down, it's going to be minus 15 sine of, not 60, 45 J. Since our vertical force on this one is going in the negative direction. Okay, so the resultant force is going to be the combination of these two vectors. So F1 plus F2 is the resultant force. Okay, so if I combine these, move this up a little bit. Oh, come on. There we go. Okay. So if I combine these, we get, combining just our horizontal components, 10 cosine of 60 plus 15 cosine of 45 I. And then combining our vertical components, we get 10 sine of 60 minus 15 sine of 45 J. All right. And so then it's best not to leave sine and cosine in this, and sine and cosine of 60 and 45 are easier ones to find. So cosine of 60 is 1/2. So 10 times 1/2 is just 5. And then we have square root 2 over 2 for cosine of 45. So 15 root 2 over 2 I. And then for this one, sine of 60 is root 3 over 2. So we're going to go 10 root 3 over 2. And then sine of 45 is also root 2 over 2. So minus 15 root 2 over 2 J. And then we can, cancel this and make it instead 5 root 3, since 10 over 2 is 5. But that's about as simplified as we can make this. So this, with the simplified 5 root 3 instead of 10 root 3 over 2, would be our answer for what the resultant force is. You could also calculate then the angle that this makes with the x-axis. So as kind of a secondary part here, we could calculate angle with the x-axis. And then that would give us, well, theta is going to be, as we saw in the last problem, tangent inverse of the y component over the x component. So this is going to be tangent inverse of 5 root 3 minus 15 root 2 over 2 over 5 plus 15 root 2 over 2. And then I would just toss that into a calculator. You don't need to, worry about trying to figure that one out without one, obviously. So yeah, there's one resultant force type of problem that we could see. So just to kind of go back through it real quick, express your vectors in terms of I and J, combine your vectors to get the resultant force, So add your I components and your J components. And then if you need to, you can also figure out the angle that it makes with the x-axis by taking tangent inverse of the J component over the I component. Okay, so that's one kind of resultant force problem that you're going to see. Now we're going to tackle one more resultant force problem with kind of a weight displacement application. So for this one, we're also going to need a picture. This one is the same example that's in your textbook. We're just going to kind of explain through that. So here we go. So third problem of the day, another resultant force one. So for this one, the picture that we're given is that we've got these two wires that are in tension, and there is a 100-pound weight dragging them down. And we are also, so these are our tension vectors. We're told that this angle is 50 degrees and that this angle is 32 degrees. And this vector is the T1 vector, and this is the T2 vector. Okay. And we are asked, what is the tension in these wires? So the first thing that we want to do is express T1 and T2 in terms of I and J. Okay, or the horizontal and vertical components here. And so we are going to use right triangle trig again, kind of dealing with this right triangle here. This angle would also be 50. And this right triangle here, this angle would be 32. So and we don't know what the tension in these wires is. We don't know what the magnitude of the vector or the length of the vector is, but we can express T1 as well. T1, if we think about this as being kind of the center of our coordinate system, if we're imposing a coordinate system here, T1 is pulling in the negative x direction and the positive y direction. So it's going to be negative magnitude of T1 cosine of 50 for the I component. And then the J component is going to be positive magnitude of T1 sine of 50 J. And then we're going to express this T2 in a similar fashion. T2 is going to be, but since it's pulling in the positive x direction, it's going to be positive length of T2 cosine of 32 I. And it's also pulling in the positive y direction. So it'll be T2 sine of 32 J. Okay, so now we've got both of our vectors expressed with their horizontal and vertical components. Now what we want to do is we know that T1 and T2 together, so T1 plus T2, that resultant force, must counterbalance the weight. So this is our resultant tension here. And then the weight we know is pulling in the negative J direction. So negative, or because it's, only has a vertical component to it. So it's in order to counterbalance that weight, these must offset this. So we know that T1 plus T2 must equal that 100 J, because it's got to be pulling up in the opposite direction to hold this in tension. So then what we can do, kind of for our third step here, is we can take actually what we've expressed as T1 and T2, add them together, and set that equal to 100J. So I'm going to take my I components and combine them. So we have negative T1 cosine of 50 plus T2 cosine of 32 I plus the J components added together. So we get T1 sine of 50 plus T2 sine of 32 J, and that has to equal 100J. Oops, there we go. Slide it over. All right. So if this is the case, then since there's no i's over here, I know that this has to equal 0. And since there's 100J over here, I know that this has to equal 100. So now I'm going to set up two separate equations. So for this one, we know that negative T1 cosine 50 has to, or actually, so that plus T2 cosine of 32 has to equal 0. So if I move this one over, we get T2 cosine of 32 equals T1 cosine of 50. And then my goal here is to solve these two equations simultaneously, since I have two variables and now two equations. So what I'm going to do is divide by cosine of 32 on both sides. Because now we have T2 in terms of T1. All right, so now we have T2 in terms of T1, and in my next equation over here, we're going to have T1 sine of 50 plus, and then instead of T2 sine of 32, I'm going to take this and plug it in. So we get T1 cosine of 50 over cosine of 32 sine of 32 equals 100. Okay. So now I can, well, I can factor out a T1 from both of these. So we get T1 times sine of 50 plus cosine of 50 sine of 32 over cosine of 32 equals 100. And now we can finally divide by this big thing on both sides. So we get that the magnitude of T1 is 100 divided by sine of 50 plus cosine of 50 sine of 32 over cosine of 32. And now we want to type that into the calculator. Don't forget to make sure your calculator's in degree mode. I know for calculus, we mostly leave it in radian mode, but this one does give us the angles in degrees, so double check. If we type all of this into the calculator, we should get approximately 85.64 pounds for T1. And then we would take this and plug it back in over here to figure out what T2 is. So for the last part here, so T2 would be approximately 64.91 pounds. So those would be the tension in the wires. And then you could also express those vectors then in real terms. So I'd have T1 from all the way back up at the top, we knew it was negative length of T1 cosine 50I. So now it's going to be negative 85.64 cosine of 50 I. And if you actually plug all of this into the calculator too, you get negative 50.05 I. And then it would be 85.64 sine of 50J. So if you plug this into the calculator, you get 65.60J. So this is our approximate vector for the tension in the first wire. And then you calculate the tension in the second wire similarly. You take the 64.91 instead and plug it in. So we end up with T2 being approximately 55.05 I plus 34.40 J. All right. So there we go. Those are some examples of vector application problems with resultant force. I'll be back on Monday, so feel free to ask any questions then or help each other out and work through the problems together. See you guys later.